Hello everyone, welcome to the video lecture on angle modulation. In this lecture, we are going to see what is angle modulation and what are the different types of angle modulation techniques. So let us begin our presentation. So coming to the presentation outline. So what are the basics of angle modulation? What are the different types of angle modulation techniques? And again, in this we have narrow band FM, NBFM and wide band FM. And next one is comparison between narrow band FM and wide band FM and their generation and detection techniques, pre-emphasis and de-emphasis, advantages and applications. So coming to the definition, so modulation means changing the characteristics of the carrier signal with respect to the instantaneous value of the baseband signal. So coming to the angle modulation technique, so in this, the angle of the carrier is varied with respect to the baseband signal. Okay. Already we know about amplitude modulation technique. So in the amplitude modulation technique, there is a certain disadvantage that the carrier uses most of the power. So coming to the angle modulation technique, so the important feature of this angle modulation technique is it provides better discrimination against noise and interference than amplitude modulation. So coming to the types of angle modulation techniques, so we have phase modulation and frequency modulation. The angle modulated wave can be expressed as S of t is equal to AC into cos theta I of t. So where AC is the carrier amplitude and theta I denotes the angle of the modulated sinusoidal carrier. Here theta I of t is known as what? It is angle. So this angle is increases monotonically with time. During the interval from t to t plus delta t, so we can write down f delta t of t as theta I of t plus delta t minus theta I of t divided by 2 pi delta t. So this, from this, we will write down the instantaneous frequency of the angle modulated signal S of. So the instantaneous frequency of the angle modulated signal is given as fi of t is equal to limit delta t tends to 0 f delta t of t. So substitute f delta t of t here and apply the limits. So we'll get fi of t, which is known as instantaneous frequency, which is equal to 1 by 2 pi into d by dt of theta I of t. So as I said, theta I of t is known as instantaneous angle of the angle modulated signal. So this theta I of t is given as theta I of t is equal to 2 pi fct plus phi c. Okay. So coming to the types of angle modulation techniques, we have two types mainly, which is phase modulation and frequency modulation. Coming to the phase modulation is a type of angle modulation in which the angle of the carrier is varied linearly with the message signal or the baseband signal, which is known as m of t. So the instantaneous angle theta I of t is equal to 2 pi fct plus kp into m of t. Okay. Here kp is known as phase sensitivity of the modulator. Substitute this instantaneous angle in the angle modulated carrier. It is given as S of t is equal to AC into cos 2 pi fct into theta I of t. So by substituting in that, we'll get S of t is equal to AC cos of 2 pi fct plus kp into m of t. So these are the waveforms. First one is the baseband signal, also known as modulating signal, which is a low frequency signal. Second one is carrier signal, which is a high frequency signal. The third one is phase modulated signal, in which the phase of the signal is varied with respect to the message. Coming to the frequency modulation. So frequency modulation is also a type of angle modulation in which the instantaneous frequency is varied linearly with respect to the modulating signal. So this instantaneous frequency is given as fi of t is equal to fc plus kf into m of t. Here KF is known as frequency sensitivity of the modulator. We have Fi of t, which is equal to Fc plus Kf into M of t. So already previously we know Fi of t, which is 1 by 2 pi into d by dt of theta I of t. So we need to equate both of them. So in case of Fi of t here, we'll substitute 1 by 2 pi d by dt of theta I of t. So from that, we'll write down what is theta I of t. After getting theta I of t, we'll substitute in the time domain representation. So after substituting the time domain representation of the frequency modulated signal is S of t is equal to AC into cos of 2 pi FCT plus 2 pi KF integral 0 to t M of t dt. So this is the time domain representation of frequency modulation. This is the waveform representation. First one is the baseband signal, also known as modulating signal. Second one is carrier signal, which is a high frequency signal. So when you look here, the frequency modulated wave. So as the amplitude of the baseband signal is increasing, its frequency is increasing. So here we are having maximum frequency. So as the amplitude is decreasing, the frequency is decreasing. So there are frequency variations in the frequency modulated signal. So here the amplitude of the FM wave is constant. We have only frequency variations. Okay, we have F max and F min in case of FM wave. So there is a relationship between frequency modulation and phase modulation. So when you recollect the time domain representation of frequency modulation, so what is S of t? S of t is equal to, so here we have S of t is equal to AC into cos 2 pi FCT plus 2 pi KF integral 0 to t M of t. So first we need to give this message signal to an integrator. After that we need to phase modulate. So that's what given here. So we can generate FM wave using phase modulator. So the first block is integrator. So the integrated signal is given to the phase modulator. Another input to the phase modulator is carrier signal. So from here, from the output of the phase modulator, we'll get FM wave. Similarly, so we can generate a PM waveform using frequency modulator. So the modulating signal here is given to the differentiator. So after that, it is given to the frequency modulator. The another input to the frequency modulator is a carrier signal, which is AC cos 2 pi FC. So coming to the single tone frequency modulation technique. So we are, as the name itself implies that, so there is a single frequency. Okay. So consider a sinusoidal modulating signal, which is given as M of t is equal to AM cos 2 pi FMT. So we know the instantaneous frequency of the FM signal, which is Fi of t. I represent instantaneous frequency, which is equal to Fc plus Kf into M of t. So substitute M of t here, Fc plus Kf into M of t means AM cos 2 pi FMT, which is equal to Fc plus Kf into AM is known as delta F, frequency deviation, delta F into cos 2 pi Fm. So what is delta F? Delta F is Kf into AM. So which is also known as frequency deviation. It represents the maximum departure of the instantaneous frequency of the FM signal from the carrier frequency. So the angle of the FM signal is given as theta I of t is equal to 2 pi integral 0 to t Fi of t. So substitute Fi of t here and do the corresponding integration. So 2 pi FCT plus delta F by Fm. So here we have what? Cos 2 pi FMT. Integration of cos is sine 2 pi FMT divided by 2 pi Fm. Okay. So here 2 pi gets cancelled. So the resulting expression is 2 pi FCT plus delta F by Fm into sine 2 pi Fm. So this delta F by Fm is known as modulation index. So this is represented as beta. So beta is equal to delta F by Fm. So substitute this in theta I of t. So theta I of t is equal to 2 pi fct plus beta into sine 2 pi fmt. So S of t, substitute this theta I of t in S of t. So we know angle modulated carrier. So what is it? It is S of t is equal to AC into cos theta I of t. Substitute theta I of t here. Then you will get S of t is equal to AC cos 2 pi fct plus beta sine 2 pi fmt. So based on the value of beta, so we can distinguish two cases in case of FM. One is narrow band FM, the other one is wide band FM. So when beta value is small, then it is known as narrow band FM. When beta value is greater than 1, then it is known as wide band FM. So coming to the narrow band frequency modulation, here what is the value of beta? The value of beta is less than 1 radian. So take the mathematical representation of FM signal, which is S of t is equal to AC cos 2 pi fct plus beta sine 2 pi fmt. Okay. So we need to expand this cos of A plus B. So cos A cos B minus sin A sin B. So cos A is cos 2 pi fct. Cos B is cos of beta sine 2 pi fmt. So beta value is less than 1. So cos of beta sine 2 pi fmt can be written as 1 minus sin A sin B. So sin A is sin 2 pi fct. Sin B is sine of beta sine 2 pi fmt. So when theta value is less, sine theta can be written as theta. So we can write it as beta sine 2 pi fmt here. So this is the resulting expression. So S of t is equal to AC cos 2 pi fct minus beta AC into sine 2 pi fct sine 2 pi fmt. So S of t is equal to, again, you need to expand sin A sin B formula. So after expanding, so this is the resulting expression. S of t is equal to AC cos 2 pi fct plus beta AC by 2 cos of 2 pi fc plus fmt minus cos of 2 pi fc minus fmt. So how you will expand to sin A sin? So 2 sin A sin B means cos of A plus B minus cos of A minus B. By seeing the time domain representation of narrowband frequency modulation, we need to conclude some points. This narrowband FM signal is similar to AM signal. So the envelope contains residual components of amplitude modulation. And next, coming to the another conclusion. So by restricting the modulation index less than 0.3 radians, the effects of residual AM and harmonic PM are limited to negligible levels. See, this is the time domain representation of narrowband FM, first one. And the second one is the time domain representation of AM. So when you look here, so all the components are same. So first one is carrier, the second one is upper sideband, and the third one is lower sideband. Except for the sign of the lower sideband, narrowband FM is similar to AM. So the bandwidth of narrowband FM can be written as 2 FM, which is twice the highest frequency of the modulating signal. So this is the phasor representation of narrowband FM as well as AM. So this is the carrier. So this is the lower sideband, and this one is the upper sideband, and we'll draw the resulting phasor. This is the resultant one. And by joining these two, we'll get the resultant phasor. So coming to the phasor representation of uh, narrowband FM. So here we have a negative sign for lower sideband. So this is the carrier. So upper sideband and lower sideband, because we have a negative sign for lower sideband, and this is the resultant phasor. So this is the block diagram of narrowband frequency modulation. So we'll draw this block diagram based on the time domain representation of narrowband frequency modulation. So when you recollect the time domain representation of narrowband frequency modulation, so it contains, look here, so it contains what? AC cos 2 pi FCT carrier and integral of message signal and 90 degrees phase shifted version of the carrier. So based on that, we'll draw this. So modulating signal is given to the integrator. So one input to the integrator is this, one input to the product modulator is integral output, integrator output. The other input is 90 degrees phase shifted version of the carrier signal. So these two are given to the summer. Okay. So one is 90 degrees phase shifted version of the carrier. The other one is the output of the product modulator, so that you will get narrowband FM. Next one is wideband FM. So coming to the wideband FM. So in the wideband FM, the value of beta is greater than 1 radian. So S of t is equal to AC cos of 2 pi FCT plus beta sine 2 pi FMT. So again, we'll expand this expansion cos of A plus B, cos A cos B minus sin A sin B. And we'll write down the resultant time domain equation using Bessel functions. Okay. So we'll rewrite the above equation for FM and simplifying the of Fourier series representative also by using Bessel function. The equation for the wideband FM will be obtained. So coming to the wideband FM. So after simplification, so you will get this S of t is equal to AC into summation n is equal to minus infinite to infinite Jn of beta cos 2 pi Fc plus NFM into t. So we'll write down the corresponding frequency domain representation S of F. So cos 2 pi Fc plus NFM t. So cos frequent Fourier transform is del of F minus Fc plus del of Fc plus F plus Fc by 2. So here you will get AC by 2 summation n is equal to minus infinite to infinite Jn of beta into del of F minus Fc plus NFM plus del of F plus Fc plus NFM. So this is the Bessel function. These are the values of the Bessel functions. So the Bessel function is represented as Jn of beta. So n is equal to 0, 1, 2, 3, 4 like that. So for different values of beta, write down its corresponding value. So coming to the properties of Bessel functions, we will use certain properties of the Bessel function. So Jn of beta is equal to minus 1 whole power n into j minus n of beta for all n. For small values of modulation index, J naught of beta is equal to 1 and J1 of beta is equal to beta by 2 and Jn of beta is equal to 0. And summation n is equal to minus infinite to infinite, Jn square of beta is equal to 1. So we will use these properties while calculating the bandwidth of wideband FM. So, and we'll draw the corresponding spectrum of the wideband FM. So, as I said, we have infinite number of sidebands in wideband FM as n varies from minus infinite to infinite. So look here, S of f is equal to AC by 2 summation n is equal to minus infinite to infinite Jn of beta. So n ranges from minus infinite to infinite. So we have j minus infinity of beta to j plus infinity of beta. So ideally the bandwidth of wideband FM is infinity because it has infinite number of sidebands. So when you look at the spectrum, it has FC, first sideband FC plus FM, second sideband FC plus 2 FM. So n will draw the spectrum for different values of n. So for the special case of beta, only Bessel coefficients J naught of beta and J1 of beta has significant values, and the remaining values are very small. So we have only one pair of sidebands, which is FC plus or minus M. So we'll write down the corresponding power. So V square by R by taking resistance as 1. So power is equal to AC square by 2. So the average power of the wideband FM is given as 1 by 2 into AC square summation n is equal to minus infinite to infinite Jn square of beta. So from the properties of Bessel function, Jn square of summation n is equal to minus infinite to infinity. Jn square of beta is 1. So the average power of wideband FM signal is AC square by 2. So this is the spectrum of wideband FM for different values of beta. So these are the spectrum representation for different values of beta. So coming to the transmission bandwidth of wideband FM, as I said, ideally we have the bandwidth of wideband FM is infinity. So coming to the practical case, overall we can write as bandwidth is equal to 2 into delta F plus 2 into FM. So this 2 FM is narrowband FM bandwidth plus wideband FM bandwidth is 2 into delta F. So together we can write it as by taking delta F common. So 2 into delta F1 plus Fm by delta F. So we know beta. So beta is delta F by Fm. So this is the bandwidth of FM signal. So this is also known as Carson's rule. So in another way, we can represent the transmission bandwidth of FM. So which is equal to 2 N max into FM. So here N max represents the largest value of n that satisfies the requirement Jn of beta greater than 0.0. That means we'll take the sidebands whose amplitude is 1% of the carrier amplitude. So we'll consider only significant sidebands. So this is the modulation index beta, and the corresponding number of significant sideband frequencies is given here. For 0.1, it is 2. For 0.3, it is 4, like that. If you take beta value is 30, so it is the number of significant sideband frequencies are 7. So this is the universal curve for evaluating the 1% bandwidth on FM wave. So as the beta value is increasing, the bandwidth significant pair of the number of significant sidebands decreases, so the bandwidth is decreases. So this is the comparison between narrowband FM and wideband FM. So coming to the parameter, modulation index is less than 1 in narrowband FM and it is greater than 1 in wideband FM. So maximum deviation is 5 kilohertz in narrowband FM and it is 75 kilohertz in wideband FM. The modulating frequencies is 20 hertz to 3 kilohertz in narrowband FM and 20 hertz to 15 kilohertz in wideband FM. As I said, bandwidth of narrowband FM is same as that of AM, which is 2 FM. Coming to the wideband FM, it is 2 into delta F plus FM, also known as 2 into beta plus 1 into FM. So coming to the applications, narrowband FM is mainly used in FM mobile communications like cordless wireless ambulance, short range, ship. So coming to the wideband FM, so the applications are we are mainly used in broadcasting. So coming to the generation of FM, so we need to generate an FM signal and we need to detect or demodulate the FM signal. So coming to the generation, we have mainly two methods, direct FM and indirect FM. So we can generate FM directly using voltage controlled oscillator. So indirect FM is also known as Armstrong method. So these are the different methods of FM generation. Direct method and indirect method. Indirect method is also known as Armstrong method. Direct method, we will generate FM using voltage controlled oscillator or else FM reactance modulator, direct FM varactor diode modulator, PLL direct FM modulator. So coming to the demodulation. So we need to demodulate the FM signal. Demodulation means reproducing the original signal. So the FM demod in case of FM demodulation, first in case of FM signal, frequency variations will be there. So the FM signal is the input to the demodulator. So first we need to convert frequency variations into amplitude variations and then amplitude variations. These amplitude modulated signal along with the FM is given to the envelope detector. From that you will get the original message signal. So coming to the different types of demodulator. So we'll use a tune circuit frequency discriminator, slope detector. So we have single slope detector or unbalanced slope detector. Coming to the phase difference detector, we have Foster-Seeley discriminator and ratio detector. So we can detect FM using PLL. We have one more technique which is known as zero crossing FM detector and quadrature FM demodulator. So coming to the comparison between AM and FM. So in case of AM, amplitude of the carrier is varied with respect to the message. Whereas in case of FM, frequency of the carrier is varied in accordance to the instantaneous value of the message. So the constant parameters here in case of amplitude modulation, amplitude will be varied. So frequency and phase is a constant. So coming to the frequency modulation, frequency will be varied. So amplitude and phase are constant. So coming to the modulation index, in case of AM, it is represented as mu, which is ratio of amplitude of message to the amplitude of carrier. So coming to the modulation index in case of beta, it is delta F by FM. So coming to the bandwidth, it is 2 FM in case of AM. The bandwidth of FM is 2 into delta F plus FM. Number of sidebands are only 2 in case of AM. So we have infinite number of sidebands and its value is depends on beta. And these are the few applications of AM and FM. So mainly we use them in broadcasting. So coming to the pre-emphasis and de-emphasis. So FM is superior than AM in terms of noise and interference. So we can achieve this performance using pre-emphasis and de-emphasis techniques. So pre-emphasis and de-emphasis, it is a method of improving system performance in FM systems. So coming to the block diagram, so pre-emphasis filter we have, and next it is given to the FM transmitter. So before modulation, we need to give the modulating signal to the pre-emphasis filter. After that, we'll modulate, and again it is transmitted through the channel. Again, it is received and demodulated. After that, it will be given to the de-emphasis filter. So why we are doing this pre-emphasis and de-emphasis means the signal to noise ratio is not uniform throughout the range. So in order to make uniform signal to noise ratio, we will boost the higher frequencies before modulation, and the opposite action will, we need to attenuate the same frequencies at the receiver. So boosting of higher frequency signals is known as pre-emphasis, and attenuating the signals at the receiver is known as de-emphasis. So look here. So FM signal to noise ratio without pre-emphasis. So see here. So this is we have a uniform signal level, and this is the power spectral density of noise. So coming to the power spectral density of noise, so at higher frequencies, this noise is more. So when you calculate signal to noise ratio, it is minimum at the higher frequencies, and it is maximum at the lower frequencies. So we always, for a communication system, signal to noise ratio should be maximum. So we need to maximize this signal to noise ratio. So that's why, so this signal to noise ratio is minimum at higher frequencies. So we need to emphasize these emphasize the higher frequencies, so that you will maintain uniform S by N ratio. So this is S by N ratio after pre-emphasis. See here, we have a uniform signal to noise ratio throughout the range. So this is how we will improve the performance of FM signal. So this is the pre-emphasis and de-emphasis filters. So pre-emphasis filter is also known as high pass filter, and de-emphasis filter is also known as low pass filter. So this is the transfer function of high pass filter, and this is the transfer function of the low pass filter, and this is the uh, representation with respect to frequency. So these are the attenuation curves of pre-emphasis and de-emphasis. So here, this vertical dotted line is frequency where pre-emphasis and de-emphasis will start. So coming to the advantages, disadvantages, and applications of angle modulation. So coming to the advantages, it is more superior than AM because of noise reduction. So when you when you recollect, so we can reduce the carrier power also. So that is also one advantage. So improved system fidelity, it is more efficient, and the operating frequencies of FM are very high, which are given by 88 megahertz to 108 megahertz. So you can transmit musical programs with higher degree of fidelity. So these are the few advantages of angle modulation. So one more advantage is so we can reduce the power transmitted by the carrier, and we can make them even zero for different values of beta. So we can make J naught of beta is equal to 0 for different values of beta. That means the carrier power is 0. So entire power will be allocated for transmitting the sidebands. Coming to the disadvantages, increased bandwidth. So bandwidth is more, and we use some complex circuits. Coming to the applications, it is mainly used in commercial radio broadcasting, television sound transmission, two-way mobile radio, cellular radio, and microwave communication also will use. So that's all about angle modulation technique. Thank you.